Hello to everyone. My name is Giuseppe Pastore and I'm going to present the paper A Closer Look at Self-Training for Zero-Label Semantic Segmentation. This work was carried out as my master thesis at Politecnico di Torino, in collaboration with Professor Barbara Caputo and Dr. Fabio Cermelli from Politecnico di Torino, Dr. Yoncin Sien from Max Planck Institute for Informatics, and Professor Zeynep Pakata and Dr. Massimiliano Mancini from University of Tübingen. Our work addresses semantic segmentation task, that is, labeling each pixel of an image with a class label. In this image, a segmentation model will easily identify cats and dogs, marking all the rest as background. But if you paid attention to the image, there was also a sofa. How is it possible to include the sofa in the knowledge of this model? Surely adding supervision also for it at training time. The standard way to do it is by manually annotating each pixel of the sofa in the training dataset. But try to think to the effort, to the cost to do this kind of operation for all images of a dataset. To understand better, try to identify all the classes present in this image. Have you got something like this? Large human annotated datasets require expensive pixel-wise annotation, and for this reason, the reduction of pixel level at supervision become even more important. In our work, we focus on generalized zero-label semantic segmentation, in which the goal is to segment the novel classes not annotated during the training. The work is divided in seen and unseen classes. The first ones identify the classes for which exists in the training set at least one annotated pixel. The second ones are the classes never seen by the model at training time, but that are asked to be predicted at test time. In the image presented before, we saw that not all the present classes are labeled, and this happens at training time. Please notice the difference with the zero-shot assumption. In the zero-shot, it is assumed that no pixel of an unseen class is never seen by the model at training time, while in zero-label, the training set includes many pixels from unseen classes, but are labeled as the sofa. The latter is obviously a more realistic scenario, as both in the commonly used dataset and in reality, there is a large amount of class co-occurrences. The task to label unseen classes at test time is called zero-label semantic segmentation. Even if the model has never seen sofa pixel at training time, it is able to predict such class at test time by learning a function to model the semantic relationship between seen and unseen classes. However, zero-label assumption doesn't take into account the co-occurrence of seen and unseen classes. The generalized setting is a more realistic scenario, as the model has to predict both seen and unseen classes, but is also more complex due to the significant performance drop on unseen classes due to the bias towards seen classes. To the best of our knowledge, only 3 works directly address the generalized zero-label semantic segmentation task, but with complex structure and mechanism to solve the class imbalanced issues. Espinet takes the task as a visual semantic embedding problem, evaluating the compatibility between the visual space and the semantic one, so that proximity translates in a semantic relationships. It's very simple, but it severely suffers from the class imbalanced issue that it tries to solve by reducing the prediction score of unseen classes by a constant calibration factor gamma that is sensitive and hard to tune. CACNet and ZS3 address the task through a more complex structure based on a feature generative approach, in which they learn generative models to synthesize features for the unseen classes so that they can train a classifier. As we saw, in zero-label assumption, a labeled pixel of training images can contain complementary information about unseen classes, but these are commonly ignored during the training. Instead, what we propose in this work is to capture the latent information about unseen classes by supervising the model with self-produced pseudo-label for unlabeled pixels. Pseudo-label is not a novel concept, and it has been used as a self-training strategy for semi-supervised learning. However, as we will see in a moment, generate accurate pseudo-label for unseen classes in semantic segmentation is very difficult, because the accuracy on unseen classes is often much lower than in the supervised case. The main contribution of our work are a self-training pipeline to obtain strong supervision for unseen classes from a label pixel by enforcing consistency constraints on data augmentations. We show that a model fine-tuned through such process progressively enhances its ability in predicting unseen classes and consequently the quality of pseudo-labels. We extensively analyzed our approach on Pascal Vogt 12 dataset, both excluding and including the background, and the CocoSat dataset, demonstrated that our model stands as the state of the art in generalized zero-label semantic segmentation. So let me describe our model deeply. As step 3, the image X and the ground truth Y with label pixel for scene classes is given to a pseudo-label generator. It is applied to a label pixel of training images to generate pseudo-labels example of unseen classes. The obtained pseudo-labels are then combined with the ground truth for the scene classes to obtain a new ground truth to fine-tune the model in this step. Differently from the SPNet that ignores the unlabeled pixels, we exploit the latent information of them and we have the cross-entropy loss computed on the unseen classes for the unlabeled pixels to the standard one on the scene classes computed for the labeled pixels. The main insight is that the pseudo-labeled pixels circumvent the need of unseen class data, holding a more balanced training set that facilitates the generalized zero-label semantic segmentation. Intuitively, the better the model is, the more accurate pseudo-label it can generate. And this is the reason why the pseudo-label generator is iteratively updated. The fine-tuned model as step D will be used in the pseudo-label generator as step T plus 1. As said before, generating hard pseudo-labels as one-hot prediction directly from the pre-trained generalized zero-label semantic segmentation model is not ideal because of the high level of noise, as we can see in this figure. The key assumption on our method is that a pseudo-label is more likely to be correct if the model predicts the same label when presented different augmented version of the same image. We call this approach consistency constraints, and it works in this way. Given an image X containing unlabeled pixels, we apply k different data augmentation to obtain a set of k augmented images. We then apply the model PT to generate hub pseudo-labels as one-hot labels for every unlabeled pixel in each augmented image, and we obtain a set of k hub pseudo-labeled masks for the image X. Then the inverse data augmentation is applied to transform augmented masks back to the original space. The final pseudo-label mask is obtained by applying the intersection operation of those k masks. In this way, we are able to filter out the pseudo-labels that are inconsistent across multiple augmented masks, holding more accurate pseudo-label. Contrary to hard labeling, we call this kind of approach soft pseudo-labeling. As anticipated, also CAGNet and CTES3 introduce a similar approach, but they generate generalized zero-shot pseudo-labels, so they include the scene classes in the search space of a labeled pixel that for sure are background or scene classes. Then, to filter out the scene prediction, they select only pixels for which unseen classes are present among the top percentage of submax activation, so relying their strength on the hyperparameter P to be fine-tuned according to the confidence of the pseudo-label generator and to the dataset. On the contrary, our approach is simpler, no hyperparameter dependent, and more effective. Approaches similar to ours has already been explored in semi-supervised learning, but we are the first to apply the consistent constraints to the generalized zero-label semantic segmentation task. Regarding the experiment, following the previous works, we evaluated our approach on two datasets, Pascal Vogt 12 and CocoSat. We followed the previous works for the validation procedure and for the data splits. The data splits are presented in these slides. Standard generalized zero-label semantic segmentation approaches perform evaluation only on pixels of the foreground objects. But in our experiment, we performed some additional experiments where the background is included among the set of scene classes for the Pascal VOC12 dataset. As train and validation set belong to disjoint subsets of scene classes, we use the following two-stage procedure for fine-tuning. We first select the best hyperparameter considering as seen the training classes and as unseen the validation ones. Then we perform training considering unseen both training and validation classes with fixed hyperparameters, so without looking at the validation set again. Following the previous works, we measured the generalized zero-labeled performance in terms of mean intersection of a union on the seen and unseen classes, as well as the harmonic mean among the two. A first outcome of the experiments is that self-training strategies improve the performance of all methods and for all the metrics. This result confirms that considering the co-occurrence of seen and unseen classes through self-training is always very beneficial. The improvements are larger in non-generative models like Spinet than in generative ones like Cagnet or ZS5. A second clear outcome is that our strict strategies outperforms every published results by a good margin. These improvements are outstanding, confirming the importance of equipping any zero-label semantic segmentation model with an effective self-training strategy. Note that the self-training approach greatly reduces the bias of the network on scene classes without requiring any calibration factor. And also is to reduce the pseudo-limiting noise, improving the performance of unseen class with respect to the other strategies. Here we evaluate the change in performance for Pascal VOC12 when the background class is included in the search space. Note that this scenario is far more challenging since the pixel of unseen classes might be labeled as background, hampering the model capability to discriminate them. Even if all the methods suffer a severe performance degradation, our strict approach demonstrates its effectiveness even in this setting. Qualitatively, we can observe the pseudo-labels and the semantic segmentation mask our model is able to produce. In this slide, for each image, GT is the actual ground truth Y, while label pixel represents the annotation for scene classes that the model sees before the pseudo-labeling. From the figure, we can see that our starting point, SPNet plus hard pseudo-labeling, detects the presence of pixels on scene classes, but the predictions are noisy, with some pixels assigned to classes not present in the current image. Our consistent constraints strict allows to largely reduce the noise, eliminating most of the pseudo-label assigned to pixels of classes not present in the current image. With more iterations, strict produces more refined pseudo-labels, where spatially coherent structures are present. This means the pseudo-label generator captures global information of unseen classes, something which is not possible to do with a single stage of pseudo-labeling. Regarding the semantic segmentation mask, in this figure is possible to see that our model correctly identifies pixels of unseen classes as well as seen ones. Moreover, it achieves a good trade-off between seen and unseen classes. For instance, on the image on the second row on the left, the DES5 misclassifies most of the pixels of the sheep, that is an unseen class, as a cow, that is a seen class, showing the bias towards seen classes. On the other hand, our model segments almost perfectly the sheep, with few pixels misclassified. This image shows also some drawbacks of our approach, meaning the dependency of the models and of the result on the number of co-occurring pixels. For instance, since plants occupy a low portion of the image, it is hard to the network to produce consistent pseudo-label for it, with consequently low recognition ability of the final model for that class. We performed an ablation study to further analyze the type of transformation applied for the consistent constraints and the number of self-training iteration on Pascal VOC 12 dataset. Basically, we focus on two kinds of transformation, mirroring and three variants of multiscaling, down, up and random scaling. This because we want them to be simple and invertible to keep the pixel matching among the transformation. According to the results shown in the table in this slide, we choose the combination of mirroring and upscaling for our final method. Another important aspect of our algorithm is the iterative self-training procedure. Here we analyze the impact of the number of self-training iterations for strict in both cases with and without the background in the Pascal VOC 12. As the figures show, for both metric and setting, the performance tends to increase as the number of iterations increases until an iteration in which the performance saturates and starts to decrease. This is due to the fact that we don't have ground truth for density in classes pixels, and noisy prediction can be reduced but not entirely eliminated by our consistency constraint. To conclude, let me summarize the main findings of this paper. We produce a simple, robust and scalable self-training pipeline to learn the model to segment classes not annotated in the training set. The strength of our pipeline entirely rely on a consistent constraints mechanism and an iterative fine-tuning. And we demonstrated the effectiveness of this method on two commonly used benchmarks for semantic segmentation, and we obtained that applying such simple considerations outperform other more complex strategies in generalized zero-label semantic segmentation. On the contrary, also some drawbacks are present. Pseudo-labels noise can be reduced but not entirely eliminated by our consistent constraint, required further study. Also, our approach depends on the number of co-occurrence pixels. It's difficult to learn the segment object poorly represented in terms of pixels in the dataset, like potted plants for the Pascal VOC 12 dataset. So, future works might exploit strategies to regularize the supervision of forensic classes based on the number of pseudo-labels generated for each of them, and techniques of weakly supervision such as point supervision to learn from noisy pseudo-labels. This slide concludes my presentation. To further details or to try strict, please visit the GitHub page at this link. So thank you for your attention.